So today we'll be talking about two AP problems, 1974 M2 and 1986 M2. These two problems cover rolling without slipping. So the first problem talk about the moment of inertia of a uniform solid sphere, mass m, radius r, and about its diameter is 2mr squared over 5. The sphere is placed on an inclined plane, angle theta, as shown above and released from rest. Determine the minimum coefficient of friction between the sphere and the plane, which will roll down the incline without slipping. So, in order to determine the the coefficient of friction, we will start with the formula force of friction equal the coefficient of friction times the normal force. So, and we know that the normal force, which is like this, give us U times mg, because the opposite force is ma. Yeah, I mean is mg, and with the angle theta it will give us U mg cos theta. So this is for force of friction. We still need to determine the force of friction in order to substitute force of friction and mg cos theta in order to find the coefficient. So in order to find force of friction, we can use the formula torque equal force of friction times R, capital R. And we know that torque equals moment of inertia times alpha. And we have the moment of inertia, which is 2 over 5 mr squared. So we'll replace that. And we know that alpha is acceleration over r. So times a over capital R. And by doing some math, we can find finally that the we can, by doing some math and combining force of friction with this formula, we'll find that force of friction is equal to 2 over 5 times ma. And we have the acceleration formula, so we'll plug in the acceleration value, so we'll plug it in and we will find coefficient of friction times mg cos theta. Should give us here. A is equal to 5 over 2 u g cos theta. And so this is the acceleration, right? And we can use that to find the coefficient of friction. So knowing that sum of forces is equal to ma, then the sum of the forces are mg sine theta This is for the force minus, sorry, back, minus this force of friction, so umg cos theta, which equals ma, and we have the acceleration, five half ug cos theta, and we will add the mass, so it's u m g cos theta. And by doing some math, we'll find the final value of u, which is u is equal to 27 tangent of theta. I apologize if I don't show the math, since I I used a lot of space, and I didn't have room to show it to you. So this is the first question A. So for B, if the coefficient were 0, would the speed of the sphere at the bottom be greater, smaller, or the same as in part A? Explain your answer. So I think that at the bottom of the sphere, this is talking about rolling with slipping for the second question, since coefficient of friction is 0. So if the ball is rolling with slipping, then the speed at the bottom will be greater, since the energy at the bottom of the sphere is the same in both cases. I mean, in rolling with slipping and without slipping. So there is no torque and energy in at the bottom here, and which leaves like all the energy going into the velocity and translation. So the speed will be higher at the bottom here at this point. Yeah. So this is the 1974 M2 answer. We basically give the force of friction formula, then we found the acceleration value using the torque formula, then we used the sum of the forces in order to find the coefficient of friction. Now let's go into 1986 M2, and let me erase this. So an inclined plane makes an angle theta with the horizontal as shown above. Solid sphere of radius r and mass m is initially at rest in the position shown, such that the lowest point of the sphere is a vertical height h above the base of the plane. The sphere is released and rolls down the plane without slipping. The moment of inertia of the sphere about an axis through its center is 2 mr squared over 5. Express your answers in terms of mass, radius, height, g, and theta. Determine the following for the sphere when it's at the bottom of the plane. Its translational kinetic energy. So in order to find the translational kinetic energy, we need to determine V, because the translational kinetic energy formula is 1/2 mv square. So we have to determine the velocity, and knowing that the sphere at the top has a potential energy of mgh, and at the bottom it will have the translational kinetic energy plus the rotational kinetic energy. So 1/2 mv square plus 1 half I omega square, and I is the moment of inertia. So this is translational kinetic energy, and this is rotational kinetic energy. And and in order to find that, we will use the moment of inertia value given here. So we'll put mgh equal 1 half mv square plus 1 half times the moment of inertia, which is given, 2 over 5 mr square times omega square, and we can replace omega by v over r square. So then we will find 1 half mv square plus, by doing some math here and removing the 2's, we will find 1/5 mv square. This r goes with this r, and it gives us 1/5 mv square. And by adding them up, it will give us 7 mv square over 10. This is mgh, which is the potential energy. And by putting v square over here, we will find 10 times gh, and the mass goes with this mass over 7. So we found the velocity square value, and we will plug it in here and find k, which will give us k equal 5 over 7 mgh. So this is the translational kinetic energy value for A1. So right now let's move forward to A2. And for A2, we know that the rotational kinetic energy, as mentioned before, is 1 half I omega square. And knowing that omega is velocity over r square, we can use this formula and find that k is 2 over 7 mgh, which is the inverse of the translational kinetic energy. So this is 2 over 7 mgh for rotational. Now I'm done with A2, and determine the following for the sphere when it's on the plane: its linear acceleration. So we gotta find the linear acceleration when the sphere is here and it's without slipping. So in order to find that, we can use again the add a new page. So in order to find the linear acceleration, we can use again the torque formula as we did before. So torque is equal to F times R, and we know that torque is equal to I alpha, and we have the alpha value, which is A over R, I times A over R, and we know that I is equal to 2/5 mr square, so we will put that here, times A over R, and all of this is force of friction times R. So force of friction is equal to 2/5 MA. Then we can do the same as the problem before. Sum of the forces equal MA, and we know that sum of the forces is mg sine theta minus the force of friction, which is 2 over 5 MA, which is equal to the mass times acceleration. And we can find that g sine theta is equal to 7 over 5 A. And we can remove the mass from all of this. And A will be equal 5 over 7 g sine theta. So this is the answer for B1. And let's scroll up. So the magnitude of the frictional force acting on it, and this is the force of frictional force. Force of friction is equal to 2/5 MA, and we can plug in A here, and we will find that force of friction is equal to 2 over 7 g sine theta. And the solid sphere is replaced by a hollow sphere of identical radius r and mass m. The hollow sphere, which is released from the same location as the solid sphere, rolls down the incline without slipping. What is the total kinetic energy of the hollow sphere at the bottom of the plane? We know that the total kinetic energy is 1/2 mv square plus 1/2 I omega square, which is equal mgh. So basically this is the formula that you should use for C, and they're only asking for the total kinetic energy, which is mgh. So we can say K equal mgh, or 1/2 mv square plus 1/2 I omega square equal mgh. So D states whether the rotational kinetic energy of the hollow sphere is greater than, less than, or equal to that of the solid sphere at the bottom of the plane. So the rotational kinetic energy will be at the hollow of the sphere greater, since the moment of inertia of the hollow sphere is greater, and it will be moving slower at the bottom of the incline. All right, thank you, and I hope that these two AP problems will be helpful for you.